And we're back and better than ever in 14-3, the ideal gas law. In this particular section, we're showing you how to use the ideal gas law, PV equals nRT, and we're currently showing you how to use that PV equals nRT to solve any of the gas law questions. We've already showed you how you can use it to solve a Boyle's law question, and now in example number 3, we're going to show you how to address a Charles's law question. So here's the question. If a sample of gas occupies 6.80 liters at 325 degrees Celsius, what will its volume be at 25 degrees Celsius if the pressure does not change? Alright, now, I always like to start off my questions using PV equals nRT. And then simply rearranging the questions to put all of the changing variables on one side and all of the constants on another side. And so in this case, notice we have the volume that's going to change because it's starting at 6.80 liters, and it's going to, and we're actually asking what will the final volume be. Our starting temperature is 325 degrees Celsius and is ending at 25 degrees Celsius. And so we're going to take the volume and the temperature, the changing variables, put them on one side, and then put everything else on the other side. So let me move the temperature over to this side, so that it's with the volume. Of course, the temperature is divided out. And then I'm going to move the pressure over to the other side by dividing it over. And so now what we're left with is V over T equaling NR over P. And just like in the Boyle's law situation, we can say the initial, which in this case is V1 over T1, is going to equal the final condition, which is V2 over T2. Why? Because V over T always equals NR over P. And so V1 over T1 equals NR over P. V2 over T2 also equals NR over P. And so therefore, these two quantities will be equal to one another. V1 over T1 will equal V2 over T2. And now let's simply plug in our values and solve. The original volume is going to be, we're going to do it over here, 6.80 liters. Now the original temperature is 325 degrees Celsius. However, we have to use the absolute scale. So in order to change Celsius into Kelvin, you add 273 to it. So 325 plus 273 is going to equal 598 Kelvin. So that is actually our initial temperature. You always have to be in Kelvin when doing the gas laws. The final volume, V2, we don't know what that is. That's what we're solving for. The final temperature is 25 degrees Celsius. So if I scratch that off to the side, 25 degrees Celsius plus the 273 changes that into 298 Kelvin. And so I'll plug that in as well. Alright, so now we have to solve for our V2. Well, of course, you're going to multiply the 298 Kelvin over to the other side. Of course, these entire terms will divide out. Over on the left-hand side here, the Kelvin units divide out. And now V2 is going to equal 298 times 6.80 divided by 598, and that is going to be equal to 3.39 liters. Now let's see if that makes physical sense. We drop the temperature. As you decrease the temperature, according to Charles's law, the volume will also decrease. Volume and temperature are directly related. So if you heat something up, the volume expands. If you cool something down, the volume is going to contract or decrease. And in fact, that's what happened. As we cooled down from 325 degrees Celsius to 25 degrees Celsius, the volume contracted from 6.80 liters down to 3.39 liters. So that makes sense. Now let's go ahead and try another example. We have Gay-Lussac's law. A sample of nitrogen gas has a pressure of 6.58 kilopascals at 539 Kelvin. If the volume does not change, what will, I should say, will the pressure be at 211 Kelvin? So notice we are decreasing the Kelvin temperature, so therefore we expect the pressure to also decrease. Let's go ahead and calculate what that would be. Now we're starting with PV equals nRT. We want to move the temperature over to the pressure. So the temperatures divide out here. We got to move the volume over to the constant side because the volume is not changing. And so I think we can safely say now that P1 over T1 is going to equal P2 over T2. And so now let's simply plug in our values. The original pressure is 6.58 kilopascals. The original temperature is 539 Kelvin. We're already in Kelvin, so we're good. The final volume, the volume is not changing. The final pressure is what we're looking for, so we have P2. The final temperature is 211 Kelvin. So now we simply need to solve for P2. So we're going to multiply the 211 Kelvin over to the other side. Of course, the 211 Kelvin divides out completely over here. The units of Kelvin divide out here on the left, top and bottom. And now our final pressure, P2, is simply going to be 211 times 6.58 divided by 539. And if you perform that calculation, you do get a final pressure of 2.58 kilopascals. And that makes sense because we thought the pressure would decrease as you decrease the temperature, and in fact it does. It went from 6.58 kilopascals down to 2.58 kilopascals. In the next podcast, we're going to take a look at using PV equals nRT to solve a combined gas law question, and then we're also going to talk about the difference between ideal and real gases. We'll see you next time.